Welcome back to our ASTR seminar series, everybody. I'm very happy to introduce this week's speaker, Alex Pope, who's joining us from the University of Massachusetts at Amherst, UMass. I assume you're also technically a member of the other 5 colleges?
Well, the 5-college astronomy department is
Okay.
the umbrella institute for all of us. Yeah.
My mistake. So Alex got her PhD at the University of British Columbia and a while back at some point in time. And after that, she went and was a Spitzer Fellow at NOAO, neither of which exists anymore. So the Spitzer Fellowship Program got rolled into the Hubble Fellowship Program, and NOAO rebranded as Noir Lab, even though that sounds way more ridiculous to say. But Alex has long been a really powerful advocate for infrared astronomy ever since the Spitzer days. And so she's an expert in galaxy evolution across the cosmic time, and in particular in dust. And I think that's what she's going to talk about today. So we're really glad to have her. And I'm glad that a lot of you in this room have been enjoying meetings with her. So yeah, I'll stop rambling and let you take it away.
Okay. Great. Thank you very much, Justin. And before I get started, I just wanted to thank everyone that I met with today, both individual meetings and the grad students and the lunch. It's been a really great day chatting with everyone. I didn't have a break all day, but it was great. I wouldn't have had it any other way. Really interesting to learn about what everyone is working on here and find connections and stuff. So thank you for that. Okay, so as Justin said, I'm going to be talking about dust or the multiphase ISM, which is a fancier way to call dust. And so I'm really interested in understanding the coevolution of galaxies and their supermassive black holes. And I use the interstellar medium as the key tracers of these processes. And if you'll notice the background image that I have here, this is one of the first light images from JWST. This is the MIRI image of Stephan's quintet. And this is my favorite JWST image to have come out so far, just because all of the different colors that you're seeing here are picking up different spectral lines in the mid-infrared. And so I'm going to be talking about how we can use those tracers out to higher redshifts. But here you see it in beautiful image format. Okay, so before I get started, I just wanted to give thanks to some awesome scientists that I've had the honor of working with. So these are all actually current or former members of my research group. I have a broader range of collaborations as collaborators as well, but I wanted to highlight these sort of early career folks. And in particular, the work that I'm going to show you today, a lot of it was done by my postdoc who just left, Jason Young, and my current grad student, Miriam Eliezer. And so you'll see some of the great work they've been doing. Okay, so just the sort of basic background here. Casey said he'd be late because he's coming to his lecture, and so I do the intro material and then save the results until I get here. So why do we study sort of the coevolution of stars and supermassive black holes? The plot on the left there is your classical Lilly-Maddow-Dickinson plot that shows the star formation rate density of the universe as a function of redshift. And this plot from Jorge Zavala is split up into the contributions from obscured star formation in red and unobscured star formation in blue. And so there's 2 things I want you to take away from this plot. First of all, the overall star formation rises and falls with a peak period around redshift 2 that's known as cosmic noon. And second of all, for most of cosmic time, that red curve is above the blue curve. So most stars are forming behind dust. So that's the star formation in the universe, but we also know that every massive galaxy hosts a supermassive black hole. And so that black hole has to grow through phases of active galactic nucleus. And so the plot on the right is just showing another sort of established relationship in the local universe. This is known as the M sigma or Mogorian relation, that shows the black hole mass as a function of the mass of the central bulge. You could also plot the stellar mass here, and you find a similar correlation, and you find bigger black holes live in bigger galaxies. And we're not actually sure why this relationship should exist, given the vastly different scales under which the central supermassive black hole and the stars within the galaxy are growing and being fed. Okay, so star formation and black hole growth, how can we link these together in galaxies? And the key is the interstellar medium. And so this is sort of the picture of our galactic ecosystem, if you will, where within our galaxy, we have a number of different components. We have the central supermassive black hole, or AGN, at the center. Throughout the disk of the galaxy, you have star-forming gas that comes from gas cooling and falling onto the disk. That gas can cool and form stars. Those short-lived massive stars will then go supernova. And some of that gas will then continue to cool. Some of it will get sent out of the galaxy in the form of outflows. And so the key here that's connecting these two processes, the star formation and the black hole growth, is sort of the inflow and the outflow of the gas, right? The gas is the key piece that links it together, that both fuels the growth and also contains signatures of these processes on it. Okay, so I already pointed out on the plot on the left that the orange curve is higher than the blue curve. So what that is telling us, so remember this is as a function of redshift, but cosmic time, half of the age of the universe is over here. And so most of the stars in the universe are formed behind thick veils of dust. So that's true in an integrated sense over there. You can also look at the plot on the right is showing you what the fraction of star formation is obscured by dust as a function of stellar mass of galaxies. You might think, low mass, high mass galaxies, is there any different? And this really nice work by Kate Whitaker shows that as a function of stellar mass, the obscured fraction is increasing quite a bit. So this y-axis is star formation coming out in the infrared, the obscured part, divided by total star formation, unobscured and obscured. And what Kate's shown here is actually 4 different redshift bins, basically from 0 to 2.5. And all these color curves, colored points are kind of following the same curve here. And so what this is telling us is the fraction of star formation that's obscured by dust in a galaxy increases with the stellar mass of the galaxy and doesn't appear to evolve with redshift out to redshift 2.5. Okay? And you can see that if you want to get down to, let's say, 50% obscured, right, where half of the star formation is coming out in the UV, you got to get below about 10 to the 9.4 in stellar mass. So that's well below the knee of the stellar mass function. So that's another way of looking at this. Okay, so most star formation is obscured by dust. Most black hole growth is also obscured by dust. So the plot on the left here is, again, another version of the star formation rate density plot. Sorry about that. Except now the previous curve that I was showing you is in black, and the green, blue, and red curves are all estimates of the black hole accretion rate density taken from infrared and X-ray surveys. And those have been scaled to match up on the same axis, but the thing I want you to compare is the shape. They're both rising and falling, and they both seem to peak around the same epoch here, and lots of the contributions are coming out in the infrared. The plot on the right is showing, as a function of AGN obscuration, this is the hydrogen column density, basically a histogram of galaxies. And so this is AGN that are more obscured are over here, and AGN that are less obscured over here. And so this is just a histogram of sources from this survey. And this work, which is looking at AGN out to about redshift of 0.8 or 1, is finding that the majority of the sample lies in this most extreme AGN obscuration above about 10 to the 24. We consider these systems to be Compton thick. So those traditional tracers that you expect at X-ray wavelengths to be signposts for AGN are even have a hard time making their way out. Okay, so both the central supermassive black hole that's rapidly accreting and the star formation in the host galaxy, both of those are just enshrouded by dust, right? Very challenging to observe at traditional sort of optical and UV wavelengths. And so we can study them in the infrared through tracers of the interstellar medium. So here is just a little cartoon picture of a galaxy where you have a central AGN with a torus around it. You have older stellar populations, and then you have younger stars growing in star-forming regions. And then that whole fluffy cloud is just kind of like the dust in the host galaxy. So how do we see these things at infrared wavelengths? So if we zoom in, let's first zoom into the central region here. So if you zoom in to the central AGN at the center, you've got a number of tracers of this AGN that emit at infrared wavelengths. So you have hot dust from the dusty torus around there. So that's going to emit at mid-infrared wavelengths. And then you also have these high ionization lines like neon 5 and oxygen 4 that need the sort of ionization conditions that you have in an AGN to be excited. In these little star forming regions, if you zoom in, remember our stars are formed out of big molecular clouds. And so you have a big molecular cloud. As those young massive stars form, they create this photodissociation layer between the cold molecular cloud on the outskirts and the hot H2 region on the inside. So here is the hot H2 region with the UV photons going out into this molecular cloud. They create these layers where you have these different tracers of different species. And I'm just gonna highlight the PAHs here. So polycyclic aromatic hydrocarbons, those are small dust grains that emit at mid-infrared wavelengths. You've also got sort of the CO tracing out here, C+, some other tracers. Okay, so that's sort of the cartoon picture of what it looks like. Now let's put some numbers on this and see what the actual spectra look like. The plot here on the left is showing a spectral energy distribution of the Circinus galaxy. So the Circinus galaxy is a local active galaxy that has a lot of star formation and a lot of AGN activity. So it's a perfect template if you want to see all the lines together. Plus, it's the only galaxy in the universe that we have the spectrum with all of the lines. So a lot of this spectrum was taken with the ISO telescope back in the 1990s. Okay, so what am I showing here? So I'm showing as a function of wavelength. So here we've got 100 microns, 10 microns. So I'm just showing the infrared part of the spectrum. And what you see sort of underlying this spectrum is this bump down here at infrared wavelength. So this is sort of the characteristic black body peak in the dust spectrum. But then on top of that, embedded is a lot of individual spectral features, right? And so each of these spectral features has been tagged according to the species that is that's causing the lines, and they've also been color coded according to whether or not the lines are triggered by star formation, AGN, or feedback, dense gas, those types of processes. So how do we know how to color code all the galaxies here on the spectrum? We just have to look at the critical density as a function of ionization parameter. I apologize, the blue and the red are swapped between these two slides. So here, blue is AGN, there, blue is star formation. But anyway, here you can determine as a function of mostly ionization potential, which lines are tracing which processes. And once you do that, then you can go and identify the lines and detect them to be able to trace these processes. Okay, so again, this is all just kind of like nearby model spectrum with some lines. Let's go out and actually look at how well some of these tracers do. Namely, we want to use the star formation tracers to trace the star formation rate, and we want to use the AGN tracers to measure the black hole accretion rate, because then we can see how these two processes are growing within galaxies. So this was work that was done by an undergrad in my group, Meredith Stone, who's now a grad student at Arizona. Using old data from the Spitzer Space Telescope. And so what she did was she took the database of all the high-res Spitzer spectra of nearby dusty ultraluminous infrared galaxies. So these ULIRGs or LIRGs, ultraluminous infrared galaxies, luminous infrared galaxies. These are galaxies that are forming stars at sort of tens to hundreds of solar masses per year, and they're highly obscured by dust. So they're selected based on infrared wavelengths. Infrared emission. And then there was 200 or something galaxies. She categorized them to whether, according to their mid-infrared AGN fraction. So how much light in the mid-infrared portion was coming out from the AGN. And she used the PAH emission, the pH equivalent width, to categorize them. And then she binned them into these 6 bins of AGN fraction, shown here. You've got 6 different bins. And she binned up the spectra to get much higher signal to noise, right? Because every individual spectrum would be a lot rattier. So these are stacked spectra where each one has about 40 different spectra that's been stacked in there. And the common thing that allows them to be each subset to be stacked is they should have similar AGN fractions. The AGN fraction was determined from the PAHs, these broad features over here. We're going to then go look at some of these atomic tracers to use them to measure black hole accretion rates and star formation rates. Okay, so in particular, we looked at the brightest line that traces star formation is this neon 2 line at 12.8 microns. You can see this popping up quite brightly. Again, the most star formation dominated is the top, and it goes down to the most AGN. So you can even see the purple line is taller than the red line. I mean, these were scaled, but just for demonstrative purposes. And then this neon 5 line, which if I flip back and just show you where these lines are, the neon 2 line sits right here, firmly with an ionization potential that's, you know, fueled by star formation, whereas the neon 5 line, find it when I'm looking, here it is firmly with much higher ionization potential in this AGN. So these lines are definitely requiring different conditions to be excited. Okay, so you can take this neon 2 line And if it's tracing purely star formation, you can turn it into a star formation rate. And you can measure this neon 5 line, it's tracing the black hole accretion. You can turn it into a black hole accretion rate. And then you can look at this quantity, which is black hole accretion rate divided by star formation rate. So this is the relative growth of the black hole to the stars within the galaxy. And here we have it plotted just as a function of the mid-infrared AGN fraction. That's just how we binned the spectra to start with. And so there's a trend. We expected there to be a trend. But what we were interested in is the range of values that we find here. So first of all, I'll point out we used a couple of different tracers. There's also the oxygen 4 line over here, which is another AGN tracer. So here we're showing both the oxygen 4 as the solid and the neon 5 as the open symbols. And so you can see there's a little bit of systematic differences there, but they're all consistent within the uncertainties. And we compared, and so what you're seeing is for very low AGN fractions, you have black hole accretion rates that are an order 1,000,000 times lower than the star formation rates. That makes sense, right? And then you go up to the strongest AGN in our sample and you find that black hole accretion rates are only about 100 times lower than the star formation rates. So relatively, they're growing a lot faster. But what's interesting here, and again, these are local ULERGs, so local infrared luminous galaxies. This sample of local dusty galaxies are spanning 4 orders of magnitude in this quantity, black hole accretion rate to star formation rate. So within this sample of 200 galaxies, you have a lot of different relative growth rates of how fast the black holes are growing and how fast the stars are growing, right? So when you just look at that, that's quite incredible. And it's surprising we even have the Magorian relation. But again, this is a very sort of fastly evolving population. They're going through these major mergers for the most part. And so this, these are kind of consistent with what we expect from simulations. Okay, let's see. Yeah.
Again, a variable, right? So I guess what's the lifetime of neon 5? Like how responsive is that to changes in the short term?
Yeah, not. Yeah.
That's good, right?
Yeah.
That means you get to average over longer some multiple
Yes. Yeah. So Justin's making the point that we use a lot of tracers, unless we're doing, variability studies where we're constantly measuring these quantities. We are getting these measures and they're being integrated over time scales. But AGN are likely to vary. And so that's a factor that needs to be folded into the interpretation. Ryan Hickox has written a lot of interesting papers on how to fold in the tracers of black hole accretion rate with the variability to try to do these kinds of population studies. In fact, his curve is one of the ones on here. It's one of the ones up here for the sample of AGN that he looked at. Yeah, no, that's a great point to bring up. Okay, good. Any other questions? I should pause for questions as I move through. Feel free to interrupt me anytime. Okay, so this was redshift of 0, right? But, most stars are forming at redshift of 2 and all the actions out there. So how can we get out there? So if we look at redshift of 2 and we go back to this spectrum here of this Racinus galaxy, with JWST, I can observe this part of the spectrum that's shown in blue. This is shifted to redshift 2. And with ALMA, I can see this part of the spectrum. And with the large millimeter telescope, which I'm not going to talk about much today, but I can answer in the questions, you can see this part of the spectrum, which there is stuff there. It's just not shown on this plot. Okay, so what you're getting here then, if this is, this is as a function of wavelengths, and so this is largely probing the warm interstellar medium, the warm dust, the warm gas, and as you go to longer wavelengths, you're moving more towards the cold ISM. And so together, JWST and ALMA can provide this complementary picture of these two sides of the interstellar medium. Okay, so I'm going to focus mainly on this part here on the left in the talk today. I did have the CO stuff in as well, but then my talk was too long, so I'm mainly going to focus on the JWST part. Okay, but redshift of 2, if you look at how much I have, okay, so I have some of these lines. I have this neon 6 line. Prior to JWST, we didn't really know much about it. It looks promising, but we don't know. You have these, in terms of an AGN line, the red ones, you have these little ones here, but I don't know if I want to write a proposal just for that. Like, what if we could go a little bit longer and detect this nice bright neon 5 line that we know we detected really well with the previous Spitzer stuff? So if we scooch back in redshift just a little bit to redshift of 0.6, you can get all the way to here and get beyond the neon 3 and 5 line. So this is very similar to what we covered with Spitzer in the local universe, since we have a really good baseline there. So that seemed like the best kind of thing to do in cycle 1 with JWST. So that was the proposal that I put together with Anna Sagina and Lynn Yan. We called this program Halfway to the Peak, because it turns out that redshift of 0.6 is exactly halfway up to the peak. And so that's a really interesting epoch scientifically, because at the peak epoch of star formation, stars are forming very vigorously in galaxies. They're evolving very quickly. At redshift 0, things have calmed down a lot. And so in between, things are transitioning, right? And so especially with tracers of understanding black hole growth relative to star formation growth, you might expect to find some interesting things in this region here. So not only is it halfway up to the peak epoch of star formation, but we get all those key lines that we wanted, which is really the first reason that we can get all the way out to the neon 5 line. So this is the same spectrum that I showed before, tipped on its side now, and then it shows where those lines go as a function of redshift. And so you can see where you start to lose them beyond JWST's reaches there. And again, they're color coded according to which process. So these were the main lines that we expected to go after. We've got a bunch of different star formation tracers, atomic lines, pH lines, bracket alpha even. We've got a bunch of AGN lines, and we've got a bunch of dense gas shock tracer from these molecular hydrogen lines. The last thing I just want to point out from this plot on the right, I've actually split up the total star formation rate density, which is in purple, into the contributions from these LERGs and ULERGs, which are these highly dusty galaxies, and then everything that's not a LERG and ULERG. So the LERGs and ULERGs are the red curve here, which starts super low. So that means in the local universe, the contribution of these highly dusty galaxies is pretty negligible to overall star formation. But as you go back in time, they strongly evolve much stronger than sort of other normal galaxies, such that, you know, by the time you get to the peak epoch, most of the star formation is actually happening in these highly dust obscured galaxies. Okay. So the science goals of this program were to map the impact of the AGN on the host galaxy, because we're getting IFU data, measure resolve star formation, and characterize the multiphase ISM. What we did was we observed 8 galaxies at this redshift of 0.6, this halfway to the peak. And the key to the selection was that we picked galaxies that we knew had a range of mid-infrared AGN fractions, similar to what we did with that stone paper, so we could go in and look at the atomic lines. And so we had previous Spitzer IRS spectra, which was R of 100. I'll show an example in a second, that we used to pre-select our targets. And then we got the full medium resolution. So this was key, having the range of AGN fractions, so then that we could test these different growths. We observed with Miri MRS, we got the full spectrum. So we did all 3 of the configurations. So that gives us 3 to 18 microns rest, resolution of 2500 PSF 0.3. We spent about 2 hours per object. So these are pretty deep observations. We got these observations, I was telling Justin earlier today, like in July of that first year when people were just getting data, which is like a blessing and a curse. Like it was super exciting. Like, yes, I get some of the first web data. But then as I was telling Justin, like Space Telescope hadn't figured out how to deal with a lot of the issues yet. And so we spent a lot of time flushing through those, and I'll show you a little bit of that. Okay, so this was what the Spitzer IRS spectra looked like before. So this was a galaxy that's star formation dominated. The reason why we knew that is because it has these broad pH lines. So these are these polycyclic aromatic hydrocarbon, and you can very clearly see them. And so then this was the JWST Miri MRS spectrum, which I don't even feel this does it justice. I need a screen that goes like all the way out here so I can zoom in so you can actually see, you know, all these little lines, right? These narrow atomic lines. There's so much power in the spectrum that's, you know, you almost miss because of the resolution. But you can see, you know, you trace the overall spectrum with Spitzer fine in terms of the pHs, but you're missing a lot of the details from these atomic lines that you miss. Similarly, here's a second galaxy. This was an AGN dominated system because it just looks like a power law, right? And so what happens when you have a very strong AGN in a galaxy, you've got a lot of hot dust. And so the idea is either that hot dust spectrum just swamps out the pHs, or, you know, earlier people thought that the pHs could be destroyed by the AGN. You know, resolve studies with JWST seem to show that you can have pHs pretty close to the central region. So it's probably more that they're getting swamped out. Okay, so we don't see anything. I mean, we detect the spectrum, but there isn't a lot of lines in there. So we think it's AGN dominated. And then this is our MRS spectrum. So again, it's a rising continuum for sure, but you can see hints of the pH sort of signature on here, and you can certainly see a lot of these atomic and hydrogen lines on here. So lots to dig into. All right, so let me tell you a little bit about what we see in the full sample.
Can I ask,
Yeah, perfect, yeah.
why are the spectra not more similar? Like,
Why is there so much variety?
well, no, like, if it's the same object, why does the Spitzer spectrum not just look like a low resolution version of the other? Why are there new features?
But there aren't really, so, I mean, the Spitzer spectra is R of 100. And so a lot of the very narrow lines just, you know, aren't, and given the signal to noise and the resolution, aren't bright enough to, you know, basically
I
be
guess
picked up with that R of 100.
Maybe it was more obvious in the previous.
Some aperture normalization issues, so, but I don't know if there's any, you know, like this stuff here is noise. In the Spitzer spectrum, that's like the level of the noise. So the noise was basically at that level. I don't think there's anything in the Spitzer spectrum that we don't see. I think it's mainly the noise. This is an interesting feature here, right? So this is the 12.6 pH line with the neon 2 line embedded on top of it. And so our measured 12.6 line was quite broad, but I think if you look at how big the neon 2 line, all of that emission was just kind of spread out within the R of 100 channels. So it makes it look, yeah. So I mean, if you convolved the Spitzer spectra to R of 100, I'm sure there wouldn't be any fundamental differences given the noise level.
Simultaneous observations or different, they're from different times?
Are they what?
Are they simultaneous observations?
Oh, no. These were taken in like.
For the AGN case, there
Ah,
will be variability.
Yes, there could be variability. I'll ask JWST to let me take these spectra every year and then we'll see. Yeah, no, you're right. There could be variability. We don't see a lot of evidence for that though. But when we dig into these atomic lines a little bit more, which I'll show you in a second, maybe we could start to look for that. Yeah.
Also, I feel like the dust would actually, you know, because the dusty region we know around like the supermassive black hole, we know that it's not like a one density, it's like a different clouds of different densities. So depending on when you actually observe an AGN, you might sometimes see those lines and sometimes you don't because of the density of the clouds, like in our line of sight.
Yeah, and what kind of timescales are those varying?
Yeah, I'm not sure right now.
Yeah. So I mean, there's a lot of different timescales for AGN that complicate a lot of this. There's not, we're kind of just sweeping that away. Yeah. Okay, so let me show you. So this is sort of our full gallery of MRS spectra that we got. You may notice there's only 7 and not 8. I told you there was 8. One of our galaxies turned out to be an interloper at higher redshifts, which we threw out because we wanted all these nice lines and we didn't want to lose them. Okay, so you can see a lot of variety here. These spectra are ordered again according to the AGN fraction increasing as you go up. So these 2 galaxies at the top in red are almost, you know, pure AGN from a mid-infrared standpoint. You can see they have, you know, they're quite different, right? This one has some lower, weaker pH emission. This one really doesn't have any. They've got some differences in their key ionization lines. You've got a lot of things. So I'm going to walk you through all that in a second. But before I do that, I just wanted to say a note about the data reduction, just because I know some people here have looked at it. The reduction is hard. It's probably getting easier. But this is MRS is an IFU, right? So you have, this is a slice in our cube. And so this is our detected galaxy. And this panel right here is showing what we got from like the pipeline. That was like, here's your reduced thing. Right, so you can see the galaxy, but you can see a lot of noise features that are equally bright to our galaxy. This is the size of the PSF, so you can see our galaxies resolved spatially, which is really cool. So we, and by we, I mean Jason, did a lot of tricks to get this data reduced. Working, you know, it doesn't matter the details, but this is the final sort of reduction that we got to. A lot cleaner in terms of the backgrounds. We're getting noise levels at least factor of 3 lower than what you get out of the pipeline, and that's quantified down here. This is showing the 1 sigma noise of an unresolved source in our spectra. as a function of the wavelength. So all these different chunks are the different subbands of the different channels. And these thick lines at the bottom are what was predicted pre-flight for the sensitivity of this instrument. These dotted curves are what we got just from running the pipeline, which is way above, like here you can see it's like an order of magnitude too high or half an order of magnitude. These solid curves that are down oscillating around the curves are what we finally were able to reach. So we were able to reach the levels for the most part that were predicted. Things are a little messy down here in channel 1, as I was talking to Justin about earlier today. Okay, so with these nice, clean, beautiful cubes and spectra, let's walk through some of the science. Okay, so what are we seeing in here? We're seeing a rich array of lines. I don't expect you to be able to read all of these little lines that are tagged above here, but I'll walk through some of them. So we're seeing these polycyclic aromatic hydrocarbons that trace star formation most basically, but also can tell you about the dust properties. Different pHs are tracing ionized grains versus neutral grains, so that's quite interesting. Warm molecular hydrogen lines that are tracing shocks, atomic lines like neon and argon that trace star formation, other atomic lines like neon 5 and 6, higher order ones that trace the black hole accretion. We also see a lot of really cool absorption features. You'll notice in this galaxy here, we've got a lot of, if you look, a lot of really interesting absorption features. I'm not going to talk about that today, but Anna Sagina is working on a paper for that. Okay, so let's walk through some of these, starting with the pause, because those are the most complex. So how do you study these broad PA features, right? So if you look at a spectrum like this, you see these nice narrow atomic lines. Those are easy to characterize. You fit them with a nice Gaussian and you're good to go. These pH lines are very complicated. First of all, they fit better to Root and Lorentzian profiles than Gaussians. And second of all, they're often complexes of multiple features. So here, what we've done is we've used this code called CAFE that simultaneously fits all of the lines that exist in these regions over the spectrum. So that includes the atomic lines, it includes the pH lines, the hydrogen lines, and various continuum components across the whole spectrum. And if you zoom in on some of these PA features, so this is the 6.2, 7.7, and 11.3, you can see that they aren't made up of single lines. They're often made up of multiples. They're sort of these complexes. And so the challenge here is because these lines are so broad and require these complexes, getting an accurate estimate of the total flux requires this kind of simultaneous fitting. There's also the added complication that you can have extinction even in the mid-infrared. And so this is the extinction curve here, which happens to have a very deep silicate absorption feature right between these two pH lines, which can mess with the fluxes as well. So you need to be very careful to correct everything for extinction. Okay, so but when you do that, in theory, you should be able to use these different pH lines to tell you about the properties of the dust grains, because these different pH lines are going to be dominated by different sizes of dust and different ionization states. Okay, that's sort of the theory. And so here's the picture we have. So this is a PA line ratio plot. So this is the PA 11.3 over 7.7. as a function of the 6.2 over 7.7. This has been plotted by a number of studies before, and people have mapped out that purely ionized PAs should lie along this curve here, and purely neutral PAs should lie along here. This is mainly from laboratory work. The nearby Goals galaxies is this cloud of gray points. So when those results came out from Spitzer, it was like, okay, they're kind of just a big cloud in the middle. Like, what are we learning from that, right? So now we put our points on. Oh, and then the JWST work that was done by the Goals team, where they were able to resolve one of the nearby ULERGs, where they have a nuclear region that's dominated by an AGN, and then a circumnuclear ring. So this is 7469 for those of you that know your phone numbers of nearby galaxies. What they found was the nuclear region was shifted significantly kind of towards the ionized region. And so they were like, we know there's an AGN in here. We know there's a supermassive black hole. This is kind of consistent with, you know, more ionized PAs towards the black hole, whereas, you know, in the supernuclear ring, you don't have that. Well, our sample is kind of all over the map, right? So first of all, our points are just scattered around the Goals point. So they're the colored points here. They seem to be more scattered than the Goals points. They seem to cover a wider range, but there does not seem to be any sort of correlation with AGN fraction. The AGN fraction, sorry, is color coded going to red. So there's one strong AGN source down here, but one's up here. Two strong star forming guys up here, but one strong one down here, right? So there's really no easy correlation here in terms of the AGN fraction. You can plot it directly as a function of AGN fraction. So this is now the ratio that's most sensitive to ionization conditions as a function of the AGN fraction. And again, the goals galaxies are just kind of scattered. You've got the ring in NGC 7469 and then the nucleus, so that's definitely increasing. But then you've got our points. And if you cover up some things, then you might conclude that there's a trend, but I don't like to do that. And especially with only 7 galaxies, I think there's a lot more going on in these systems, and especially when you're looking at, you know, full galaxies, even if the overall mid-infrared emission as determined by the pH equivalent width seems to be dominated by the AGN hot dust, it doesn't seem to be having a big enough impact on the relative PA ratio. So it's not changing the composition of the PAs. Or what we see of the PAs. The plot on the right shows another ionization sensitive ratio. This is now the neon 2 to neon 3, right? So neon 3 is a higher ionization potential to neon 2. These are both mainly star forming lines, but this one's a little more higher ionization. And there you do see a little bit more of a trend if you ignore mainly this yellow galaxy. But even within the gold sample, you see a little bit more of a trend. Again, neon 3 is also picking up a lot of star formation, and so none of this has been corrected for that yet. Okay, what about the warm H2 region, warm H2 lines? So these warm H2 lines are sensitive to like dense gas, and when they're looked at relative to pH lines, they can tell you whether or not they're sort of dominated by shocks. So this is another popular diagnostic, which is the ratio of this one of the H2 lines to one of the pH lines. And there's sort of this threshold that's been determined as the shock cutoff, where galaxies above this line have higher enhancement of this shocked gas relative to their overall pH emission, which is overall star formation. So you can see some subset of the goals galaxies are up here. These are, again, mostly major mergers in their coalescing phase, but only one of our galaxies sits marginally above this curve. And so for the most part, this sample that we've looked at redshift 0.6 during this transition period halfway to the peak of very dusty galaxies don't appear to be very shock dominated. And again, we're kind of sitting around the scatter of all these local ULORG points, right? Okay, what next? I showed you that we could actually resolve these emission lines. And so what can we learn from that? So if you just focus on the left panel here for a second, you can see this is essentially the size of the PSF for at the very longest wavelength of our spectrum. So what we can do is we can extract different aperture spectra and then compare them and see if we're actually seeing different diagnostics. And then in this paper, we compared mainly the star formation diagnostics because those were the ones, this is a very highly star forming galaxy. And so those were the highest signal to noise. And so this plot on the right is actually showing on top of just the galaxy mid-infrared image, contours showing these different star formation tracers. So we have a couple pH lines, argon 2 and neon 2. And the idea is that, you know, you can look for different morphologies, which might tell you differences about star formation timescales. And we found a hint, a very marginal hint, that the pH was a little more extended than the atomic star formation lines, in particular out in this region of the galaxy, which could suggest different star formation histories if the pH lines are sensitive to star formation on longer timescales than the atomic lines. Does that hold for the whole sample? Not really. Okay, so for the whole sample, we did something slightly different where we measured the whole spectrum in a small, what we call the nuclear aperture, and then in a larger total galaxy aperture. And then we did the ratio of neon 2 to PA 6.2, so a ratio of 2 of those lines in our bigger aperture compared to our smaller aperture. Right, so if both of those lines are equally tracing the same parts of the galaxy at all radii, then you would expect everything to just be consistent with the 1-to-1 line, which they are for the most part. This galaxy is maybe, you know, a little bit more neon 2 extended. This one's maybe a little more cut 6.2, but given the uncertainties, I'm not sure there's a lot there. And we've looked at this plot for every single ratio that you can think of, and there's nothing that really stands out. I will point out that this analysis is slightly different than the previous analysis because we're averaging, right? Whereas the previous one, you know, we were looking for an asymmetry. We were able to pick out this asymmetry on one side, which would be washed out if you average over the whole aperture. But I don't know that there's anything glaring in terms of the spatial distribution. But the spatial distribution does allow you to do one thing that's really exciting, and that's kinematics. Because we have all these really nice narrow atomic lines, we can go and then basically, you know, look at it on a spaxel by spaxel basis and determine the velocity field. And so this is the kinematic map from argon 2 at 7 microns. We picked this line because it's the brightest line in sort of the shorter wavelength end of the spectrum, and so we get better spatial resolution, but it's also a really nice bright line. It traces star formation really well. You can see this beautiful rainbow velocity curve, which you can quantify with a V over sigma, and you find that it's rotation dominated stable disk. So this was kind of a surprise. I think we might have, in bonus science in the proposal, written this is an idea, and this has been something fun. My student Miriam is working on the whole sample, and this is what we find. So the middle column is the rotation curve, where it's going red to blue from positive to negative velocities. And you can kind of see rotation in all of these from a distance. Maybe not this one, I wouldn't claim rotation in these ones, but all the other ones, you've got the size of the PSF there. The resolution isn't quite to do like a complicated rotation curve analysis, but you can quantify the V over sigma and determine that most of these are rotationally dominated. So this is another interesting result, because again, these are dusty infrared galaxies. They're halfway back to the peak in this transitioning period, but they're these nice stable rotating disks. And it doesn't matter if they have a black hole in them or not, right? The ones that are strongly dominated by the black hole down here, these are kind of ordered by AGN fraction, seem just as much rotation as the other ones. So that's kind of interesting. And lastly, how do we quantify that black hole accretion rate? So I had mentioned before that we have this really nice neon 6 line that sits on top of this pH feature. Prior to JWST, we hadn't really looked at this very much. We had looked at this a little bit with ISO, but Spitzer's high-res mode started here and went to higher wavelengths. So we didn't actually have any spectra of it. And so this was kind of fun and surprise. And there's only a handful of galaxies in the whole universe actually that have black hole accretion rates measured from this line. And now we've measured it for a bunch of other ones out at higher redshift. So here's what the line looks like. It looks like it's complicated because it's embedded on top of this pH feature, but you can decompose it very nicely. You can get a very nice flux for this line. And then you can plot it. Again, you can turn it into a black hole accretion rate. So neon 6 for your black hole accretion rate. I'll use neon 2 for my star formation rate. So this is like a ratio of black hole accretion to star formation. These diamonds, okay, maybe there's more than a handful, but like a handful and a half, right? Two handfuls. Those are all the galaxies that have neon 6 measurements. Those are nearby local ULERGs published by Veja. And you can see that, you know, they show a pretty wide scatter here. They don't show a lot of trend with infrared luminosity. And we've got this galaxy down here. I'm only showing one on this plot because I'm still working on the numbers for the rest of the sample. But this is really interesting because this is this galaxy down here, FLS1, which is one of our most star-forming galaxies, right? It's only 17% dominated by the AGN in the mid-infrared, but we can still measure the black hole accretion rate from neon 6 and put it on this plot. And of course, it's like an order of magnitude lower because it's a much lower black hole accretion relative to the star formation in this galaxy. So I'm working on getting the rest of the sample on here and sort of populating where they are in their relative growth states. All right, so I've kind of like thrown a bunch of results at you, and now I'm going to throw a long list of what I think it means or what I've just told you. And I don't actually know what it all means, so I'd love to hear some thoughts if people have them. So the pH line ratios show a broader range of conditions than local ULERGs. Okay, that's not very controversial. There's no evidence for very strong shocks from the H2 to pause. The line ratios that probe ionization conditions don't seem to show strong correlations with AGN fraction. Maybe this means most of the line emission is from the star forming regions regardless of the AGN strengths. We want to look a little bit more at the spatial resolution. Star formation is spatially resolved. There's some instances where they might be tracing different parts, but you know, largely you're getting the same extent. The argon 2 line is a great measure of kinematics. And when we do that, we find the sample is mostly dominated by rotation, which is different from local ULIRGs, different from their local counterparts. And neon 6 looks to be a promising black hole accretion rate tracer, even in weaker AGN. And so kind of putting this together to try to see like, what is the picture that's emerging of these redshift 0.6 ULIRGs? They seem relatively chill compared to their redshift 0 counterparts. So what does that mean? They're not really violent mergers. They have this solid rotation. Their supermassive black holes are active. We can measure the black hole accretion rate, but their energetics, you know, even though we detect them with high fraction in the mid-infrared, the energetics might not be driving the overall galaxy line ratios. And so we're still working on this interpretation, but, you know, we're hoping to get this slew of imprint papers out sometime this year. Okay, so let's see. I have a couple minutes left. Yeah, okay. Any questions before I move on? Okay. Should I finish in like 5 minutes or like 10 minutes? I have 2 options.
Somewhere between there is good. I don't know.
Okay.
Whatever seems.
Okay, I'll do a little bit on the higher redshifts and then just maybe, okay. Okay, so we've been focusing here at redshift of 0.6, right? Where the dust obscured star formation is clearly dominating, galaxies are evolving very strongly. But at some point, right, as you move out in redshifts, the unobscured star formation is going to dominate. But you can probably just see from this picture that where that happens is a little bit fuzzy, right? These curves are very broad. We don't actually know. These data points are all over the place. So there's still sort of a lot of uncertainty in terms of what's going on. So you can look at, I showed you this already, the fraction of star formation that's obscured by dust. As things shift to less obscured galaxies, you would expect that this curve is going to shift over, right? That you're really going to need the highest mass galaxies to have the most obscuration. Okay, so let's look at that then. So I'm going to zoom in here at a redshift 4 to 5 in this sort of, you know, transition region between obscured and unobscured dominating. And on the left here, I'm plotting the same graph I showed before, which is the fraction of star formation that's obscured by dust as a function of stellar mass. The green curve is this Whittaker relation that I showed you before from redshift 0 to 2.5. And now in blue, what I've shown you is the results from the Alpine survey, which is between galaxies between redshifts 4 and 6. Now, the key thing about this sample, and these are from stacked measurements, so this should be sort of an unbiased measurement of this quantity, even though the sample itself is probably biased. And that's because the Alpine sample are selected as UV galaxies. And so the fact that they have a lot of UV emission, right, or less IR emission, could very much be a selection effect, or it could be the redshift evolution. So we don't really know, right? So the UV selected galaxies at redshift 4 to 5 that we've looked at, the fraction of obscured star formation is lower than the redshift 0 to 2.5 galaxies. It could be a selection effect, but we find very clear examples like this little galaxy here, and there are many others, but this is the one that I work on, so it's the one I'm going to talk about, nicknamed AZ9, that have tons of dust and exist at this redshift range. So this is a fun little galaxy. So I said I've talked to a bunch of people today and said, I'm not going to talk about LMT because we haven't done a lot with LMT. We have detected a few little gems, and this is one of them. And so we looked with the Aztec camera at one of the frontier fields cluster to see which of these galaxies are heavily dusty. And there's this known multiply imaged system in here. And we were able to image 2 parts of it, extremely low signal to noise ratio observations, but we confirmed it all with ALMA later, so it's all good. But this was really cute. We detected these 2 multiple images with exactly the right ratio of magnifications, because the lensing map is very well known for this cluster field. So that was really nice. So that was enough to ask ALMA to give us a bunch of time to look at this galaxy in more detail. Because at that time, we didn't actually know the redshift. We thought it was around 4 to 5. It was a photometric redshift. And so we needed to get the redshift, and we also need to localize the position to confirm exactly where it is, because the beam was very big from the single dish. And so this is the image plane, and this is the source plane, because this is a gravitationally lensed galaxy. And so now you can see this is the galaxy in HST. So it's like, you know, maybe a nice disk there, right, from this blobby black thing. And then down here, offset, are all the contours from ALMA, from various dust continuum measurements, but also from C+. And you can see the centers of each of those as little X's there. And so yeah, we detected C+, that gave us our redshift, perfect. This nice line that just happened to fit right at the end of the band, but it's bright, so there's no risk that it's wrong. But we can also get, like we did with the previous example, a velocity map. And this one we were able to model with 3D Barolo to get the actual velocity map and all the parameters of the rotation. Okay, so what is this galaxy? I've told you a bunch of different things about it. I'm just going to skip Andy's stuff for a second. What's the deal with this galaxy? Well, first of all, this is the stellar main sequence. Star formation rate is a function of stellar mass. This galaxy lives way, way, way down here. Relatively low masses, maybe not low masses for JWST times now, but very low masses for being directly detected in dust emission, because nothing is getting directly detected in dust emission down at these low masses at millimeter wavelengths. So this is very, very low mass on the main sequence, but it's highly, highly obscured. Like 75 to 80% of the star formation is coming out in the infrared, and that shouldn't be the case from the obscured. And it's a nice, stable, rotating disk. So usually low mass galaxies are supposed to be like less stable and more violent, right? And usually low mass galaxies at high redshift are supposed to be lower metallicity, so they should have less dust. But this is just a good example that, you know, you can have quite a high redshift galaxy 1.5 gig years after the Big Bang that's been able to produce a lot of dust and create this nice stable rotating disk. So I just use this as a nice counterpoint for, I think there's still a lot of work to be done out at that redshifts 4 and above to be able to look for these obscured systems. Some of the ways we can do that is with, you know, the LMT and ALMA, but some of the way we can do that is with JWST mirror imaging. I don't think I really have time to go over this right now, so I'm going to skip this. This was mainly for Casey, who's in here, so I'll share it with him later. Okay, so I think the jury's still out in determining how prevalent galaxies like AS9 are, but I'll just finish with this, which is, I've been talking about how we can do so much great astronomy over here for galaxy evolution and so much great astronomy over here for galaxy evolution. But what about all this stuff in the middle, right? We have no telescope that can access this. And so this is untapped territory for the next probe mission that NASA is currently competing for. So I'm involved in this concept called PRIMA. PRIMA is designed, it's a new NASA concept that would launch in 2033, and it's designed to fill this gap with spectroscopy over the whole range. So all of these tracers, doesn't matter what redshift you're at, you can just get them all. And not only can you do the black hole star formation, coevolution stuff that I'm really excited about, but you can also do other science, like study the atmospheres of planet forming disks, right? You can measure water lines in planet forming disks. Those exist at these wavelengths too. You can also study the very detailed characteristics of the dust properties that I kind of alluded to being much more complicated. Okay, so I have a few slides on PRIMA that I'm just going to skip over so that I'm not just going too far over. So I'll just end with my summary, which is that, you know, the ISM is just sort of this rich place for information about the evolution of galaxies. This JWST Miri spectra is extremely powerful. You can simultaneously measure all these different pieces of what's going on in these evolving galaxies. And what we find for these ULERGs at redshift 0.6, which are halfway back to this peak epoch, so I expected them to be kind of, what did I expect? I expected them to be much more sort of turbulent, a lot more, I didn't expect any ordered rotation. I expected a lot of differences in terms of the line ratios and ionizations, in terms of the AGN fraction, and we're not really seeing a lot of that. So that's kind of interesting. They're sort of settling down. I think observations of the ISM of galaxies at redshift greater than 4 are biased by very small and disjoint samples still. I've literally been saying this for my whole career, except it used to be greater than 2 and then greater than 3, and now it's greater than 4. Like, we're inching up there, but you know, there's still a lot of work to be done. So this AS9 galaxy is a perfect example of a very obscured low mass system that sort of defies what we expect. So I think the future is really a far infrared probe like PRIMA, to be able to probe both this warm and cold ISM over all cosmic time. So I'll stop there. I'm happy to answer any questions.
Some questions.
I can ask you a question.
Old people first, I guess.
Yes, thank you. The spectra are lovely, but you don't seem to ever detect bracket alpha.
Yeah,
Is there a
good.
reason for that?
So I was telling Justin this earlier, so in general, the longer wavelength channels are the most noisy. But channel 1 has been a little bit of a trouble for us, not because, so a lot of the issue with beating the noise down in these spectra, you know, is the astrophysical side, but also the detector characteristics. And in channel 1, I think there's a lot of non-Gaussian noise left in there. And so I don't know that those spectra, I mean, if you looked at the spectra I had with the uncertainties, we aren't doing quite as good as we expected. And the program was designed to just about detect bracket alpha. So we do detect it in a couple of the galaxies, but not in all of them. But I think that's just a noise level thing. And I think that's the limitation with that. Yeah, the one galaxy that we do detect it in very clearly, the star formation rates are consistent with what we get from the other lines. We get a nice redshift that's consistent. But yeah, bracket alpha was gonna be our go-to, like, you know, this is our systemic velocity, this is, yeah. Yeah, so that and the PA 3.3 are kind of seem to be lost in channel 1. Yeah. Good observation.
Limitations. I wonder like how much of uncertainty is actually produced because of the limitations in the resolution.
For bracket alpha.
I don't know, I mean, like for those, like the narrow lines over there, for example. I don't know what is the resolution over there, but I'm guessing it should be low.
No, it's 2,500. Or
500,
2,500.
but
It's-
then it'll be something like, you know, 300 kilometers per second.
we're
But
not,
the winds of the lines are really high, but like, for example, the one on the right, it's like a really narrow one. I was wondering how much of these are actually like broken by resolution.
I don't.
Androids are aligned very precisely because it's so.
Yeah.
Like, even though the spectral resolution is only 100 kilometers per second, you can find the center of that line much more precisely.
Okay, but then the flux, well, because like the some of those lines are like they're really close to each other, so you need to find a smart way of, you know, getting rid of those.
Sorry, which lines are you talking about?
Like, for example, the one on the right, they're like a two, like a narrow lines over there. No. Yeah, no, just the big one.
Oh, this PH line?
Yeah,
This
and
is
there's
broad.
another one. Like, they're like a two lines over there, yeah, it's not one.
Yeah, well, this is the 11.3.
So the single line,
Yeah, this is one of the PA complexes here. This has got this is one of the complexes that has like a little, a big one and then a little side one. Yeah, so this is broad. This is very, very spectrally resolved.
Those are molecules.
Yeah.
They're not.
oh, yeah.
Ionized lines, right?
Yeah.
Molecules.
All these ones that are just like straight lines in here that show that those are all the atomic lines, but as
Okay.
Justin said, you know, those are bright, you're getting the positions very well in the fluxes, yeah. Yeah.
Like that I was confused. like-
Yeah.
I have a question about design.
Yeah.
Does the some millimeter initial offset from the optical?
Yeah, that's what I was. I brushed over this stuff fast. That's what you kind of see here, right? So this is the optical. Yeah, maybe the disk, I don't know. With the center of that, these are the center of the dust emission and some panels here. So they are definitely offset, which is even more confusing why the velocity file is so nice, right? So there's the velocity, there is the center of the HST, and there's the contours of the dust emission. Yeah.
Are you worried the stellar mass is underestimated because your stellar mass is coming from this part, so the mass is
Yeah.
from this part?
Yeah, I mean, this was, you know, the referee asked, we did Seagal fitting and all this, right? And so, you know, there's definitely a bit of hand waviness in the stellar mass, but it can't move it very far. So it's, you know, there's a lot of scatter in the main sequence there. And so it's possible that the stellar mass, what did you say, overestimated? Underestimated. underestimated, right? Yeah, so it's possible that the stellar mass is a little bit higher, but even if it's like, that, it's still kind of. You wouldn't say anything different about it, so yes, I completely think that it could be uncertain.
Can you estimate the dynamic mass from the carbon tube? See,
Yeah, so we did that. I forget. It was more, it was fine. Yeah. It was the usual ratios, we estimated it, and then stars are 10% or something, it's all consistent. Yeah, I think that was in Andy's paper, so I skipped this work here, so I had a grad student, Andy, who did CO follow-up and N2 as well to try to really dig into the ISM conditions, and he did a dynamical mass from the CO stuff as well. Yeah. The one thing we don't have is a detection in the Rayleigh Jeans tell of the dust for this, because all of our detections of the dust are up in the peak, and so we don't have a really good like pure dust mass estimate. We just have extrapolated from the SED, and so we did this 3 millimeter observation of the CO, and we didn't detect the continuum in that one, and so we don't have that. So it'd be nice to have that, but yeah.
All right, well, let's thank Alex again.
And I just wanted to say one more thing, because I talked a little bit about Prima, which I'm very excited about, which is going to be the telescope for the future. And I have some Prima stickers. The grad students want one, because I always bring some with me today. I can give you one. If that's okay, Justin.
We're not cool enough.
All right, thank you.
I didn't know if some of the grad students were leaving for the meeting right now or just leaving.
Okay, let me just.
Yeah, I know. It's like the whole department meeting with the department head, physics and astronomy.
Go get this thing.
Never. It's like mandatory though, apparently.
Yeah.
Apparently, I was gonna ask if you were gonna be there.
Yeah.
It's not like they're taking. Or anything.
Yeah.
I actually want, can you?
Yeah, I wanted to see the.
Coming in for